everyone. In this session, we are going to have a talk from eminent expert Dr. H.K. Sardana, who is Chief Scientist in the Central Scientific Instruments Organization under Council for Scientific and Industrial Research at Chandigarh. And he is the head of the computational instrumentation. He is basically an electronics engineer and he is also having an MBA. His area of expertise is in the field of pattern recognition, image processing, infrared, seismic signal processing, and medical imaging. He has written a lot of papers and published it in the esteemed SCI index journals, more than 30, and also he has filed patents as well as have been granted patents of more than 20 in numbers. He has also undertaken various research projects in these particular fields. So he'll be telling us regarding the upcoming research areas in the field of image processing in this session. I request him to kindly highlight the major aspects related to image processing and what are the research fields in this particular area.
Thank you, Dr. Syal. Can we connect to that presentation? Okay. Good morning. I don't know how many institutions are. Okay, 9 institutions. Okay, with some introduction by Dr. Syal about me, and now I wish to share with you what at CSIO we have been doing in terms of image processing. I'm not sure whether they have basics on image processing or.
They are from multidisciplinary area, so it can be started from the basic level.
Okay, so I will spend only few minutes to talk about digital imaging, image processing, and then try to take off, in fact, for research areas that we have been doing, and in fact take a few research case studies that will help you understand how an image is formed right at this early level and then used as applications. So what is an image? And precisely we are talking about what's a digital image. While I understand everybody in the audience would have some mobile camera holding on to some high resolution, high definition image acquisition for their personal photographs and all that. However, what are the scientific and industrial or other sectoral applications that we can consider? First of all, let me tell you that image is more like a kind of graphical representation of the scene. If you see that, if you see the screen now, can you just switch? Yeah. So it's more like a discrete representation of a continuous spatial scene that you and me are enjoying in terms of entertainment in general, but at times for our own day-to-day life, navigation, reading, writing, doing any kind of job all the day that we do. So what do we do with digital imaging as such in terms of applications, particularly the engineering applications? So if you see that, on one hand we have a kind of scene, left corner, if you say left bottom corner, if you can see how I am pointing, I don't know whether you can see the left bottom. It just shows some kind of object in the environment. And then we have illumination. Illumination, you understand, we understand normally daylight, we have sun as the source of illumination. And then our eyes in general, for us, for all living beings, we have eyes. And for an industrial or any automation system, we'll have an imaging system. Say it could be a camera in general, but there are many methods of acquiring images. Particularly those of you who have undergone some medical treatment, they would know there are X-rays, there are ultrasonic imaging, there are CT images, and there are laser images in other industrial application. There are range images, there are stereo images. So there are many kind of images. But by and large, to simplify the situation, we try to discretize as we see on the right side. If you see on the right side, we have some approximated acquisition of a digital image, wherein just to highlight the discreteness, a graphical background is projected there to let you know that image is not as original as you see, as or as natural as it is in the natural environment. So in the computer, in the digital domain, we have a discrete image, and that is where our problems and that is where our applications start. So with that digital image in the virtual domain, we have, if you see that, lot of applications would require a lot of processing, and the processing in general would mean what information, what knowledge, what purposeful data can we acquire, can we obtain from that image. So just to give you the feel of one unit as one pixel is showing, left hand side showing a picture of an animal, and then a small portion of that just zoomed on right to let you know that one unit, atomic unit of an image is called a pixel, where one pixel carries the property of that particular spatial coordinate, say x and y. So that is how an image in mathematical terms is represented as fxy, and in terms of discreteness, again it remains fxy. However, the x and y become the coordinates of the image. So you can understand that there is a discreteness, there is a finiteness in terms of the atomic level unit size that is pixel in an image, and also the overall image size that you normally know in your cameras. We have 10 megapixel camera or similar quantification of the overall dimension of the image. That shows how the total number of pixels are carried by the image you have acquired from a camera. It might be a square image, it might be a rectangular image. Accordingly, the m into n size of the image, that is number of pixels in, say, horizontal side and also in the vertical side, or rows and columns, together define the overall image size. So now moving on, you can see the images shown here in this picture, in this slide, are different, though they appear to be from the same scene. So you will see, depending upon how nicely, how accurately we acquire an image, say the first image is just showing black and white. So for the same scene, we have only the information of gray scale, that is intensity of each point in the space. And mind it, as you can see, most of the discussion that we are doing here is about two-dimensional images. That is, it has only x and y coordinates, as I stated earlier. However, the scene as such is three-dimensional. So with the limitation of the dimension as depth, now we have a limitation of the gray scale, that is only black and white. So at times in strategic applications, when we have, I forgot, there could be a situation like infrared imaging, where it won't be even looking like the way we all look at the images. In this case also, gone are the days we had black and white cameras. So now we have color cameras, so we have color inputs. But as such, the first image shows only the gray scale. So if you were looking for some colorful information in that image, that will not be possible. Now in the second one, you see really colors. So it is a red, green, blue color image, the way we call it RGB. That means we have some information of redness in that particular pixel. We also have a greenness of the information in the same pixel, and in a way we have blueness of the same pixel available through the camera, through the sensor, through the imaging acquisition system. So in a way we have three attributes available for each pixel. That means we don't have just fxy, we have maybe rxy, we have gxy, we have blue xy. That means we have three scores of the same pixel x and y coordinates in the space. We have a little bit more information as such. Now the third one, it says there are 4 samples per point. There is one more point which probably tells you about the environment in which the imaging is taken. But in this case, as you see, depending upon alpha, there are 4 parameters. Fourth parameter is alpha. It is an indication of how the space between the scene and the sensor is behaving. You can assume it as a kind of transparency. Suppose it is transparent, then you will have no value of alpha affecting RGB. However, if it is alpha available, then you can see the images available on the third column is quite different, but it is still the same scene. So that is how, depending upon how we acquire, the first level of information defines what best you can acquire, what best you can apply from that image. Okay, so now you understand that with some limitations of the acquisition, even humans with all kind of sensing capabilities and intelligence that we all carry, we have limitations. So these limitations force us to have a lot of image processing, and that is where we get into research, largely on the early level image processing, and then on the upper level, as we call it, the higher level, wherein we actually use the information in the engineering application, medical application, and many other sectoral applications. Now, so what are the tasks we have? As I said, first task is to make it worth human interpretation. So many of the medical images, particularly, or forensic images, are meant for human consumptions. So for example, you go to a doctor and looking at your x-ray, he decides whether you had a fracture or not. So that is some information enhancement, as we call it, primarily for human consumption. So these applications are largely offline. They are not automated. They are meant for bringing the best that you can visualize. So they are particularly meant for higher and higher and better visualization. Of course, largely it depends on what best you had acquired in the image. So it is not going to add any more information. However, it is going to make it worth visualization by a human being. Now, the second focus remains in research is the processing in terms of storage, transmission, and representation. They may be for later use, they may be for archiving. For example, fingerprints in your biometric systems are meant for storage. They may be even available for transmission across the channel, and then maybe they are represented in terms of, say, biometric, some kind of extracted information which would be used in terms of matching. So matching your score for how accurately you are putting your thumb or finger before a biometric system. So it's just an indication that the early, we call it early or low level to medium level image processing applications do not normally take care the last, as I mentioned, matching the higher level applications into action. So the early focus remains in terms of how best we can preserve the information that the image carried, or how best we can enhance it for human consumption. So that is where the focus remains on these two tasks. And then there are always gray areas, whether low level imaging is the processing level, or there is a medium level processing where we do a lot of transformations. You will see a lot of spectral transformations, wavelet, Fourier, and many other transformations that we try to use in terms of getting analysis, getting extraction of useful features, as we do humans try to extract features for any recognition task or matching task or inspection of objects. So therefore a lot of computer vision applications will have image processing applications, slowly from lower level to medium level to higher level, as we classify in terms of those who study the subject will understand. But largely computer vision is another term to see that there are various stages of image processing. Now, as I just said, low level, medium level, and middle level or high level, you can very well see that lower level means image to image transformation. Middle level means image to attributes or features, in simple terms we can say, which extracts some useful parameters from the image. And then higher level is the understanding, using those attributes to match, to get a result from a biometric, for example, that it is you that who is standing before the system and putting his or her thumb or finger. Or in terms of, say, robotic navigation, it may be that a robotic system is carrying a camera, and while moving it is acquiring a scene information and trying to match where the objects are or where the obstacles are, and also where the passage or the freeway is available. So it's an autonomous navigation as application. So probably with these three, you can understand there are three basic large levels, or you can say three tire or three gear systems that image processing follows. Now, as I mentioned, there are various levels, there are various steps involved in it. So briefly, I'm trying to give you some kind of applications. Say many of you are aware, which is like transmission and storage, image compression. Most of the images stored on Facebook or WhatsApp or all kind of applications that you see are always compressed, because they are not scientific applications. They are only meant for storage and generally human consumption. On one hand, I said doctors and forensic experts might like to have the best of an image processing, the lot of visualization tools, and enhancement of the scientific content of the image. But for entertainment and many normal human consumption, particularly trading off with the bandwidth available to you, you might have to do a lot of compression. So one of the research area remains as image compression, particularly in terms of storage, transmission, and a common man's consumption. Although you will see situations where tools like Facebook or others are asking you whether you want a full resolution storage, or sometimes you are permitted to have low quality. Even YouTube will ask you whether you want high definition or low definition. So in terms of transmission capability and bandwidth available, image compression remains a big research area. However, this image processing is entirely a kind of a separate segment, not meant for any automation applications. Now, other applications are into recognition. If you see that recognition applications are largely the higher level applications, like human beings, animal beings, try to recognize the objects. What do? They have a very quick analysis of the scene available before them, and then they can locate the number of objects, the particular objects of interest, and any inspection level requirements that they have to do. So you will see the workers in an industry, factory, or any level of jobs that we all do, whether they are at, as I said, worker level, or even at your level, faculty level, while you are doing reading, writing, study, education, medical, all set of these applications. We particularly, we all meet people, we recognize people. So we have a, you can say, a kind of exorbitant levels of intelligence that we have acquired a number of objects since childhood. We have learned a number of objects, and we can recognize and manipulate them to all kind of activities that we can do. So image acquisition, as this slide titles, can end up with object recognition and description of those objects for automation. So mind it, the way humans do may be so naive and so simple for you. For a machine, it's like just like a child learning to know how the objects are seen and how they can be described, how they can be recognized. So let us not assume that a particular situation like humans perceive, or even a child sees the scene in an unknown environment. You can imagine a child with 6 months age, 1 year age, and 2 years age, how much a child learns. Accordingly, the image processing and object recognition, largely the subject title is pattern recognition, wherein we learn, we make the systems learn the way the objects are to be recognized and manipulated if required. Next, please. Yeah, so now, as I mentioned earlier, the low-level processes may have enhancement. As you can see, an image on the left has some kind of visualization, while the same image with some kind of processing has made certain things more visually available. A decision can be made on the grains that are seen, and any other measurements. So there are tasks that we can perform, but at this moment it is showing that enhancement of early level images may be because of poor lighting, poor environment, and any other reasons that the imaging system might have. So image enhancement remains one step immediately after this is again the lower level, early level image processing factor. So I'll have to quickly move on. Now restoration is another term. These are all basically individually they are the research areas one can take. They are chapters in a course on digital image processing. They are independently research areas that one can do. This is just a flavor of what image enhancement is, and now there's another term called image restoration. Now restoration is something similar to enhancement. However, the restoration is what it is trying to do is it is trying to achieve as good as with knowledge of the a priori information or any other modeling that you can carry out. So this is a very advanced research area. In almost all situations we have this problem. Because of the imaging system, as I mentioned, it is not fully 3D at all. In many situations it is 2D, and there's an environment in between the scene and the source of illumination, and also there is a third point, that is the sensor or the camera. So with these three things interacting with each other, we find that the image acquired is not as good as original. So there are various efforts and various research approaches which try to restore. Not that it's not that a particular scene should be good looking. The purpose is objectively it should be restored to the original. If there was a defect in the original image, there must be a defect available in the restored image. So this is another research area that again it lies in the lower level image processing, because it is still generating the image for an image. Now, as I gave you example of biometric research applications, you will see that morphological processing is another level wherein the image is still looking like an image. However, it is no longer looking like a grayscale or no longer looking like how you see your thumb. It is giving you, in fact, it is giving you enhanced level of processing wherein you can see the lines, see the contours for your thumb or any finger pattern. So this is a kind of morphological processing which is more at a pixel level processing, where it enhances very local information to a boost level wherein matching. In fact, not just matching right now, it will have another level of higher level of transformation where feature descriptors will be formed, and then biometric matching is possible. So this is again at a lower level to medium level. As I said, it's a kind of transformation, though strictly it is not called a kind of spectral transformation because it is still in the time or space domain. But the term in this case, where an image drastically changes and uses local pixel level information to enhance what we call morphology. So it changes the texture, it changes the morphology of the image in very close vicinity. And as you see, at times it is enhancing it to white color, or it is enhancing it to black color. So it's making the image very logically, you can say, depict the finger patterns. So that is what we call morphological processing. Now, in terms of mechanical engineering, segmentation of objects, or in general physical applications where we try to get rid of the background, if you want to see the larger set of objects, the finite number of objects in a scene, we do segmentation. As you can see, some operation on the above is showing some kind of poor segmentation because of the shadow. I don't know whether such details are visible to you or not, but the segmentation is completely a logical description, similar to the biometric logical thumb impression that you just saw. Segmentation gives the similar kind of object level discrimination from the background. So the background is gone now, only the foreground is visible. So the foreground shows the objects. Now you may find it easy to count them. However, for a machine, for a computer, will have to do a lot way further. But segmentation by and large remains a turning point in digital image processing, wherein the success of recognition, object recognition, object level success of any digital image processing depends largely on this area, that is segmentation of images. And that is where there is a demarcation from low level to middle level, because now you can segment each object separately as an image, which is no longer the size of the original image. So you may have, say, 10 people or 10 objects in a particular scene. You might like to divide the image into 10 separate sub images, and these images are created, you can say they are kind of child images generated from the original image, and they carry largely the number of images, you can say probably is carrying the number of objects information also. And then of course at the moment it doesn't know what object is there in that image. Mind it, you might find it easy to know what object it is. The machine is working like a child born a few months ago, and it is trying to learn everything. So imagine there are a lot of work to be done on training and learning. However, at the moment we are talking about imaging and the segmentation step and how it separates the objects from the background. Now, what is this now? What are we doing here? How can we recognize those objects just we saw in terms of segmentation? Now, if there were two objects, the kind of objects you saw, and if we were just doing length and width as the classification, probably not always, but as an example in a class, we could say that if length and width could be the two features of those objects, of course we'll have to find out by some image processing method that how we will actually locate the length and width in that sub image we segmented just before. If at all we can do it, probably this diagram shows that the objects, if you can see, are clustered. If you had seen various images of the same scene, you might have found some variations in each image, minor variations will occur. And if you see in those situations, the same two objects are acquired and their measurements are taken, considering all the statistical variation in intensity and pixel variations in terms of errors that can occur in segmentation and all, and in terms of length and width that you could find, you will see that the two objects might confuse each other, and you might not be able to segment, or you may be able to segment. If you see the left cluster here is showing some circle, and the right cluster is showing some, actually in this case we have three objects. So it's showing triangle, circle, and square as three objects. These are not the objects, these are the depiction of those three objects. Now, maybe the left bottom object is clearly separable because of its dimensions, because of its features, but the other two objects are confusing. So merely by two features, it's like if I ask by height and weight of a person, would you be able to recognize each person in a class? Probably no. It won't be possible to, it will be confusing using only just two features to classify a number of objects, or in this case say two features to classify three objects. So that is where the difficulties lie. That is where the transformation features, middle level transformations after the segmentations become necessary. So object recognition, pattern recognition, scene description, and various transformations you will see in other domains than time and space are middle level image processing research. And at this moment we just recognize, we just acquire the features from the sub-segmented images, and we try to make ourselves ready for the next level, that is representation and description, which becomes high level data. At that level of next level, as I show next slide, as you can see here, wherein the object has a clear boundary, the object might be described as a chain. In this case it's showing a chain code. So, or this is just elementary method of describing an object. However, there are many methods. This chain code is a very elementary method of trying to, you see how badly or how crudely the object is described, and the purpose is also to make it as robust, also as robust as possible, so that the next matching levels do not have errors. So representation in a description like a chain code or a Fourier transform or a wavelet coefficient and whatnot, it could be a kind of list, you can say a small matrix out of a larger image that we acquired. We might call it a kind of object level representation, and a description. We call it representation first as a kind of, you can see first, as you see in this case, we have tried to approximate the object. So we have tried to represent the object in a simpler way so that it is robust to matching. That means we make a compromise that the object is no longer as nice as it was in the original situation, but is more like a simpler state, right angle kind of object with only 90-degree turns occurring, so that the errors, the noise that occur in any image processing early steps could probably be handled. Many of you might like to debate how accurately it will be able to do the job. Yes, there is an error we are introducing, but there is a quantization. You can see another level, right level description, which is slightly different, wherein we use a 45-degree also as a code. So we might like to describe, now in a way we are trying to make a compromise of how we can represent an object crudely. You can say like a child play toys, how accurately they describe the true objects in the real situation. A child learns from the toys. So we're trying to approximate a real object with the similar crude representation. Mind it, the purpose here is to make the processing robust, so that while truly whether we achieve the robustness or not, that again remains a research. And once we choose this representation, we describe it as a code. So every image, whether you're in terms of matching, quickness, readiness, could be a kind of a list like this code. This code is formed actually by traversing clockwise from a starting point. Those details I can skip here, but the point is that it becomes a kind of like a mobile number you have. If you can see, there are codes for each orientation. Accordingly, you can have a 9872805, that kind of number for an object. Similarly, you have a similar number for your fingerprint. So you can see now with this level of processing and description, finally with a number of steps, we might be able to describe an object as a code, as a you can say index number, and from the database of information we might like to match it. Now mind it, you can imagine with this kind of description you might have a lot of wrong numbers, and that is all possible as errors, and we should be ready for that. That is where the challenge of research is, to maximize the matching and minimize the errors. Now let's see now, probably at this stage I like to stop and give you some two examples at least. We have up to 1 o'clock. Okay, so we'd like to give you two case studies in two major sectors. So I'm stopping here as far as the fundamentals are concerned. So I'm going to give you a kind of a major sectoral application. A sector here is, say, agro sector. In this case, I'll be touching only two sectors. But before I take, I can give you, we are working on underwater imaging. We are trying to explore the whole universe or world under the sea. Imagine what is lying under the sea. And we are working on strategic application where we work with infrared images. We try to detect vehicles in terms of strategic application, whether they are tanks, whether they are trucks, whether they are army vehicles, those kind of applications, detecting them. We are working on hyperspectral imaging that will be similar to the one which I am describing here for food and other agro sector applications. We are working on medical applications, which I'll take another example after this particular one, wherein we use X-rays. So X-ray, ultrasonic, infrared, multispectral, hyperspectral, there are n number of spectrum bands that you can use for acquiring images, and they are not all as simple as human visual band that we use only red, green, blue. So we are comfortable only with the visual band that starts with violet to the red vibgyor, the color spectrum that we are familiar with. But you will see we have a large number of applications which take care of other spectrums, other radio spectrums available for many other applications. So for example, we are taking two case studies. This will take the color image processing. So let's see so let me give you a quick overview. I will use only the pictures to let you understand better. So let me give you, okay, what is this kind of slide showing? What are we seeing in this slide? So as a problem definition, these are rice grains. If you thought the rice grains are all white or gray, that's not true. There is a color element in each grain. Though a very nice, sound or healthy grain might appear as gray color, however, many other, particularly if you see other inorganic matter that you see in rice grains, there are grains with red color defects. There are grains with discoloring of the basic healthy grain. There are grains with chalky, of course, that is extreme white color, which is also a kind of unhealthy. There are rice grains which are damaged, which still have some color other than gray, black and white. And there are grains of other variety which are not desirable. So this shows the color requirement problem of grain classification. Now there are other pictures in the same slide with the less or small size of the grain. I hope they are able to see. So they are broken. Now you see the grains available in a public distribution system are not full grains. They are broken and they are officially permitted. Big broken is something like 80%, 3/4 of a grain. Then there is a small broken. You can see more or less about half the size of the grain. Then there is an organic. Organic means it's like more like a powder now, but it is still 1/8 of the grain size. Now mind it, what is the problem here? Now the problem is, given a sample of say few grams, not the whole truckload, not a shipload of grains, that also could be a problem. But for a sampling situation, as under the BIS standard, we are expected to classify a sample of grain with say about thousands of grains available in a 20-gram sample. Each grain, like a class of 1,000 students, each grain to be evaluated, classified, with given a full dimension, classified whether it is a sound grain, it's an inorganic matter, or it's a red grain, or a discolored, or chalky, or damaged, or admixture. Not or, now and it could be big broken, it could be small broken, it could be organic. So in terms of sizes, it could be full size, it could be broken, that is 75% roughly, it could be half size, it could be 1/4 size. So there are 4 size based classifications and there are 6 color based classifications. Now mind it, it is like ending of the classification. It's a class within a class. An object, a grain could be sound and also red at the same time. No, sorry. So once it is sound, we consider it is perfect. So ideally it could be sound, full size and no color defect. But other 9 classifications are some problem in terms of size and some problem in terms of color. Now this is the image processing problem now. This is not a low level problem or a high level, this is an application. This will now take you a journey of whole number of steps that are required. Now I'll just show you the steps. Okay, what is this step? This step shows how we will acquire the image. You could have used a camera, you could have used another environment. We chose for some good reasons to have image acquired through an official, desktop scanner. Now, desktop scanner gives you very high quality, no environmental problems. Once you cover the scanner, there is no noise from the outside, there are no shadows. The black sheet that we evolved gives us a very good background, so it is easy to segment the grains. All these were the reasons that we used flatbed scanner. So this shows how the image acquisition step is undertaken. Now next step. So I'll give you the algorithm only through. Okay. Now what is this? This shows that images acquired from the scanner are quite good, and the black background. Whether you see it or not, the black sheet that we used, once we use it again and again, it is dirty. So this black is not jet black. This jet black is not a zero black value. It is still having some shade. Okay, but still it's comfortable for human consumption, but we have a machine to use. So we need to segment it. There are some situations where it's dirty with a lot of usage of grain powder. It becomes some gray color, you know, and might create noisy background. So it required some pre-processing. What level pre-processing? Some analysis of histogram, which at the moment I'll have to skip, but it is just looking at the population. If you see, this histogram is a kind of diagram, is a graph which shows on y-axis it shows the number of pixels, and on x-axis it shows the intensity values. So it shows basically two peaks. One peak showing the population of grain with varied level of intensity, and the other shows the population of the background. So which is more? The bigger peak shows not the rice. The bigger peak shows the black background, because it's largely the earth, and the population of rice is just lying on that ground earth or black sheet that we used. So that small peak shows the rice. So it sounds simple. Probably we have to segment these two, make a value. It's like a value of a threshold marks to a class. We decide something middle value, say 50% or 128 intensity value, somewhere in between, to segment that rice grains from the black background. So if we do that, we get rid of the left peak. That is, all background which is not perfect black is eliminated. And then what we see, well, to you it might look similar, but this is actually a black and white, perfect black and white. The black is jet black and the white is just a saturated white. Whatever white color we want, which is all the same. All pixel values are same now. But what do we do? Have we lost the color? No. We'll come back to color a bit later. At the moment, we are looking for dimensions. We want to see the physical size of these objects. Okay, so as a case study, now, but there are problems. We find some objects closely touching each other. We'll see how nicely we can segment or not. To give you the background analysis, it shows that through analysis we are able to segment those objects, and in this case the objects seen are actually in gray color. Back to the gray color. We have eliminated, we have shown we have superimposed the indexing of the objects extracted in the previous stage. It is showing as if there are roll numbers, index numbers for each grain, and there are cross showing the center of that object, as if we are able to pinpoint each object. But as you can see, some objects are still coupled with each other, like some friends going together always, never separating from each other, just because of hand spray of the grains on the scanner. So these are the challenges. Now we apply some algorithm here to separate those objects. We have, again, this is called water shedding. Some algorithms which try to segment the closely segmented, closely touching objects, similar to, doctors doing surgery to separate the twins at time, conjoined twins. So this is that kind of surgery we have to do at times. But this surgery is not manual. We have algorithms, and how far we are successful is similar to the success of medical professionals. So we try to do that and see. You will see now this shows the overall picture, but let me zoom it to give you how nicely we are able to do or not. Okay, we are successful, but not successful all the time. There are still stubborn pairs which are not separable. Now we'll have to discard them in our analysis, assume that such a rice doesn't exist. There is no rice which double the thickness of a grain, normal grain size. So statistically we can eliminate. It's like if you find a score 120 out of 100 by a student, you will imagine that there is an error here. So like that, you will have to do a lot of wisdom at each step. But this shows partly we are able to succeed in separating some of the grains from each other, and like that the whole image carries about 1,000 of such grains depending upon the resolution chosen for the scanner. Now assuming that we are okay, now we try to see what is the labeling here. That numbering that you saw earlier Now you can see each one living in their own house, dwelling unit. Though still you find there are some living together. There are two of them together, at times. So either their length will go abnormally high, or the width will go abnormally high, or many other parameters. So in a way, we'll have some ways to reject them. So in a way, not all grains will be analyzed perfectly. Some of them will have to be eliminated. But this shows the numbering. Probably you can see the numbering, the indexing of each grain. Okay, so far so good. Let's move ahead. Now what do we do? With that, do you think a computer can understand what it is? Computer is more like a donkey. Doesn't know even what this object is. Has never ever seen this object. It's asking a newly born child, the day he starts responding, you ask, what is this? He doesn't know anything. So, okay, but the application demanded that you give us the number of such grains, that too in terms of weight. So imagine we are doing only 2D. They wanted us to give us weights of those grains. Now, okay, how do we do? We try to see, badly of course, to see what is their density in terms of gram per projected area. So new definition of density, which is gram per unit area of the image, not volume of the grain. We tried to do it just for some calibration. So as you know, some of you might know, the chalky grains are the lightest. So you find that 0.000724 gram per millimeter square. We took some 420 grains, all chalky, as per the expert labeling, and then try to weigh them and then see on an image what is their gram per unit area. So like that, we used the known grains for calibration as far as density was concerned. This is nothing to do with image processing, but shows that it required all samples to be brought together and then imaged together, and then their area was calculated. As I didn't tell you, we find a number of parameters for those, not just length and width of the grains. We find area, we find perimeter, we find convexity, we find length to width ratio, we find a lot of parameters we will see later on. But there are a lot of features that basically 8 features we do for the dimensions of the grains. So based on that, we could classify their density, so that later on, once we know the number of grains available in each class, we could multiply from the area, we could find some estimated grammage value of each grain classified. Now, what do we do for colors now? For colors, there is a research area you can note down, that is from the images are not actually processed in red, green, blue. There are color models. Particularly this one is hue, saturation and value. Basically it's like coordinate system. You don't use coordinate system. We sometimes use spherical coordinate system, we sometimes use cylindrical coordinate system. Similar to that, this is actually a cylindrical coordinate system from the RGB, which is, you can say, Cartesian coordinate system. I mean, those details one can find later on. So in this case, actually the color is shown as an angle between 0 to 360 degree, and saturation is shown as a numerical value between 0 to 1, and intensity. So saturation is the saturation of the color, okay, and the color value is shown as an angle. Okay, how much color is the saturation of that color? Rather, what is the color is the code between 0 to 360 degree. Okay, so red is on one angle, say 7 to 25 in this case. Now mind it, this red is the red grain, rice grain red, not the tomato red. So we classified all red grains together, we classified all discolored grains together, we classified manually. We have to do a lot of work. Mind it, there is a lot of manual work. We took all chalky and see how badly they perform in terms of color. H value, that is the angle value. That value is between 0 to 360 degree. And sound color, sound grains, the damaged grain. So we'll find there's a lot of overlapping and there's a lot of range available for color. That means a color lying in red is also lying in, say, discolor, or a color is also lying in chalky. If you see the large range of sound grains, it has all the colors in it, say 10 to 300. That is where we said the seemingly black and white grain is having all colors in it, basically. So anyway, these are the challenges. And similarly, we found the values of saturation and value is actually the average value of the intensity of particular pixel. That is the normal grayscale intensity value. It's like an average score. So these details will remain a question for you later on. But to quickly get into the core research issues, so what do we do with that? Do you think with that knowledge, and if I know how each pixel in a grain is distributed, so we try to make a rule-based classification. We thought, but it is again manually trained system. Manually trained system will mean a human being will decide, okay, based on my analysis or maybe a few persons analysis or a bit of statistical analysis, we could do something like admixture grains or red grains are probably distributed by these rules, like we did rule for length, width, weight, etc. to classify people. Again, it is a rough and crude classification, because human beings are unable to measure, to see all parameters at a time. If I give you all the parameters, say length, breadth, area, soundness of a pixel, sound number of pixels in a grain, discolored number of pixels in a grain, damage number, mind it, probably you are getting that now a grain will have all kind of pixels in it. It's like each grain will have some number of pixels as sound, some number of pixels as discolored, some number of pixels as damaged, some number of pixels as chalky, and some number of pixels as red. And depending on some percentage you can define. It's like somebody may ask you to classify complexion of people, whether the person is dark, whitish, or fair, or black, or whatever. It is the same thing we are doing here. So we try to give a percentage that, okay, if this percentage plus this much of percentage is lying, probably the classification is discolored or damaged and whatnot. Like that we classify. This was a kind of only 2-3 parameters at a time in a rule-based situation. Now you can see the poor the rules, the quality is also not that good. So what is the best classification here? Probably we got 86%, 88% for chalky, 86% for sound. So because some chalky was easier relatively and sound were many in number. So see, we could see chalky means because a grain which is chalky is having large number, it is almost whitish. And sound were because we were able to tune our training to more sound grains because they were largely available in numbers. You see 3,437 grains were available as chalky, as sound, and very small number, admixture 16 grains, and organic only 10 grains. So our training also depends on number of grains available. You will see human training and neural network training that we did also later on dependent on the number of samples. So all the training depends on the number of samples available. That is also one of the conclusions that we had, and that is why the reasons you can locate that very bad accuracy of say something like 10% for damaged grains. Okay, so that is again the same thing for in a graphical base. Now this shows neural network approach. You may not be able to see the figures, but I'll show you classification when we used in terms of neural network. We tried to compare the same number of features used for rule based and also for neural network. We could see that we use small number, we try to optimize the number of features. We use basically less number of features here, and we try to train. While we could train to reach more than 70-80% or at times 100% accuracy, but when you test them, you find that these features are not able to test well. That means the validation again may be as bad as 10% for say inorganic, or again because the number of samples available is not too high. So neural network also cannot be trained if there are less number of not just features, less number of samples. Okay, so with that I'll have to skip this, and we try to enhance the number of features. We try to increase basically more number of geometrical features. Mind it, we had the same 5 color features, and we had 8 of geometrical features for the size of the objects. So we could have a little more improvement But still organic, damaged and red grains, which were very small in number, were far from acceptability of even 60% accuracy. So this shows a case study in a way. You can make some conclusions here and keep them with you for questions. I believe I may come back to these conclusions of what goes wrong and what goes the best in such application. But in terms of some other aspect of this application, in terms of say processing, you might have, I gave you examples, the length. See a particular grain touching 10 millimeter of length or even higher in terms of breadth, say 2 millimeter. So there will be situations wherein the odd sizes might come, and that is where we gave you example of that water shedding problem. So you could also plot each one parameter for each grain like a graph. It's like a performance of one parameter for the whole class. So it shows that sometimes these are additional parameters available for a rice milling plant. So I'll skip this discussion on this so that we can have this coming up again in questions. Let me take you hold on to your question probably, and I will keep this available and give you a small other application of medical nature. So medical application now, for medical applications wherein we don't have anything like color image processing. We are now using, now this topic might appear new, may not be known. So most of you might have visited a dental doctor, probably many of us nowadays. So this project, this application is to automate the analysis. So I'll show you again the pictures so that it is easy for you to appreciate. Okay, now it's no longer that nice rice grain image that we enjoyed a little while ago. We have an X-ray now. What can you do in this X-ray? This is called lateral X-ray. It's like a side pose. Now the side pose means it has everything about your face, everything everything in terms of bones, everything in terms of structure, but everything embedded as two-dimensional image, not three-dimensional CT. Okay, so we are also working on CT of such images, but minded CT doses become the inhibition, and the radiation dose are also limited. You cannot have CT images again and again for a patient. So largely this analysis, though we have worked on three-dimensional cephalogram analysis, but this traditional work is on two-dimensional. Now what do we have to do? Okay, let's see more. Okay, this shows how a patient is positioned into what is called vertically at a erect position of 90 degree and sideways perfectly, so that you don't get a clutter on an X-ray, because side pose is being taken, and that too for a 3D object, 3D facial structure inside your face. So it requires a perfect alignment. Okay, so that's the way the cephalostat is taken. Otherwise, it's similar to the X-ray. Now there are landmarks. Landmarks are more like like cities in a map. You don't need to know these landmarks, but largely I can say there are soft landmarks and there are hard landmarks. The soft tissue landmarks are on your skin, what is visible outside, and there are hard tissue landmarks are inside the face, inside the structure. Now soft tissues are taken because you want to know, you want to have best of your smile, you want to have best of your looks. So the orthodontics are trying hard to make a smile on your face. So that is the basic job they are having. And outside appearance cannot be improved unless there is an inside improvement. So the hard tissues landmarks are to be measured inside the skull, inside the lateral X-ray. So there is a list of such landmarks on both sides. Now, okay, these are some medical details for those landmarks. So there are hundreds of such landmarks that are used to now find out facial features. If you are looking for outlook, these are the features, but these are not the features that you and me understand. These are the features that the doctors understand. How do we know them? How do we find them? These are the landmarks on the territory of your face, inside, outside, both. Okay, so okay, some of them visible here. If you can read it, there are named like letters: S for Sella, N for Nasian, O for orbital, P for Porion, PO again for Pogonian, P for Menton. Okay, this is a terminology. A for A point, B for B point, like that. These, some of these landmarks are shown. They are located on the geography, if I call that, or territory, if I call that, on your lateral X-ray. They are actually marked on three-dimensional skull. While the doctors learn, they learn it on 3D, but with the limitation of radiation dose that you can put. And nowadays, of course, we are using cone beam computational tomography, CBCT, wherein the dose is nominal. So people are working now. One of my students who completed PhD on this topic on 3D is also completed. So that's, there is a work on that. It's a very edge level technology. Now, but for this exercise here, I am showing you automation of these 2D landmarks. Now, how do we do? Otherwise, manually, you can imagine doctors do this way. They do all kind of manual tracing. The engineers know how they do the curve tracing on a glass with light illumination. Any question? From? Okay, shall we continue? Okay, so you can imagine a doctor is marking it on a tracing sheet or a computer screen nowadays, similar to the reverse engineering copying that we do for drawings. So it's a reverse engineering process, measuring a kind of X-ray as a drawing, similar to the rice grains that we were doing automatically. Here, doctors do it manually. So we developed a manual product to enhance and give them a kind of tool for looking these landmarks, and they can mark and make measurements. So the simplest of image processing would be to open this image in an environment and create, database for landmarks, give instructions, store landmarks, and that's all. That will be manual cephalometric analysis and provide these graphical tools to make measurements. But that won't be much of image processing. Now that will be graphical job, graphical tools to provide measurements, and then database. Now what we did was we went ahead. We tried to do it automatically. Now what is automatically approach? Let me show you the algorithm. How can we do? What is this portion of the image? If you notice this, there was a tool which was positioning the nose of the patient. If you go back and see, this is that, sorry, here is a tool which position, I don't know if you can see something on the nose. There is a machine landmark that is fixed for each patient. It's like capital of a country. It's like you want to go to any place in the country like India, you just first land into Delhi. So you first land to the Nasian point. That is a fixed point, and we call machine landmark. So we try to first locate that, because this is not going to change. That is the assumption. So we do now see the lot of pattern recognition. We have stored this from the machine that the doctors are using, the hospital is using. If the hospitals change the machine, this will have to be changed. So we stored this pattern and we try to locate it in the X-ray. Now can you see that? The same thing shown now on the overall lateral X-ray. Now we run it. What do? We located that. We located that black first in the image. In every patient, we can locate that easily because that is not carrying the person. The facial cephalogram might change, but this is something like never changing kind of portion of the image. So we are easily able to locate that. Now once we locate that, we understand that probably we have got to that main region, black region. From there, it's like once I reach Delhi, I know how far is Chandigarh, how far is Bombay. Then we have regions. Although within that region, the landmark might vary. Your landmark and my landmarks will not be same at the same location. So there is a red region for each group of landmarks. you can see region 1 showing Ogonian. Okay, Porian, sorry. Region 1 is having Porian. Region 2 is having Sella. Region 3 is having B Point, Pogonian, Menton. Anyway, the point is that region 3 is having a number of landmarks. Region 4 is having 2 landmarks. Region 5 is having another landmark. Region 6 is having one hard Nasian tissue point and then a soft tissue and Nasian also. So it has the same Nasian 3 landmarks, 3 closely spaced landmarks. Region 7 is having another landmark. Now, if like we know these are like states of a country in which you can find the capitals. But the problem is the capital is not known. It varies from person to person. That is the problem here. It's not a fixed capital, fixed kind of map for each person. The map is changing, but the basic structure remains the same. That is the underlying assumption. So what we do, we try to locate those points. How? We further divide the region, say region 3 or 4, where we had a landmark, Sella. So within that region, we try to we try to make a sub template so that within that template we'll find out a particular structure where it is. It's like tip of the nose, for example. Once you find the nose, you can try to find the tip of the nose. Similarly, it is on the ear, close to ear. There's a landmark. So within that bigger window, we search further for finer landmark location. And that is the strategy or algorithm, you can say, we can find out a hard landmark through template matching, similar to the machine landmark we found starting at the nose level. Now, for some of the soft tissues, can you see the upper lip and the lower lip, which is a soft landmark? This is a point again. Upper lip is a point, a single point on the lateral X-ray. Similarly, there is a lower lip. Now, this is now you can see if we can do a mathematical curvature analysis and find the peak. Again, peak is oriented orthogonally because the person is on the side. The peak is on the x-axis. So if we can do that, we can do some soft tissues, and that's where the strategy was. Probably you can see here now the sub-segmented image shows a canny edge detector. So the segmentation is done by contours and edge detection algorithms. This is another segmentation research area. It remained hot during 1990s to 2000, and now more or less it is matured, but I cannot say it's perfected. It still has errors depending upon the type of images you have. So now this region goes into further finer and finer region and locates that curvature, and on the curvature we find the maximas and minimas. Accordingly, from the soft tissues you can find those upper lip, lower lip, and also from this side you can find other landmarks wherein the bony structure is available, and inside you can have, so some landmarks are found through template matching and some landmarks are found through contour detection, edge detection, and using mathematical definition of those. So now you can see, depending upon the location or each landmark, the strategy is different. Maybe we find it through edge detection or we find it through the template. So we make a mix of both approaches together and see now the red, if you can see, the red landmarks are found using template matching. Okay, because the edge detection is not appropriate for those landmarks because the structures are very confusing. So we take a statistical base and try to locate the center of that template as the landmark. And for the green ones, you can see they are based on edge detection or contour detection, wherein the peak points, as you can see, those tip point, upper lip, lower lip, and valley above the chin, and the chin itself, and just a point below the chin, even a Sella point at near the nose. Near the ear. Okay, so even within the bony structure, at times we have used the edge detection approaches. So this shows how landmarks could be automatically located, minded for an orthodontics it's not an easy task, because it will take hours to first acquire an image or trace it manually or trace it on the computer graphics workstation, and then make marking on them, and then go on zooming it, zooming down, and etc. And that is where the approach lies, and there is a need for automation. So I've already described the algorithm, so I'll skip this algorithm of region detection and then point detection, which is largely the template matching I told you earlier, wherein we first detect the larger region and then the finer region. And again, it is a region. The center of that region is assumed as the landmark. Mind it, we can't find a point through template matching. We actually found a region. So in terms of performance, these were a number of patients, and then you can find the publications on this. Various versions of this basic approach have been published now in our through our laboratory. Once you find locate for Google Scholar, you will find this publication and even versions of this publication. And some results are indicative of you can have as high as 95% of accuracy of landmarks. Depends on how you define the accuracy. Sometimes the doctors define the accuracy as within 1 millimeter or 2 millimeter. So we had defined accordingly, and we got accuracy of some of the landmarks as high as 95% and as low as sometimes 45% also, say orbital, but largely others are acceptable to them, says about 80%. So that is where the recognition rate, they call it recognition rate now rather than the location accuracy. Recognition means you are able to recognize the landmark closely, nearby, to a position, say about 1 mm. And this is actually showing some details are available. Again, those details will be better seen through papers that you go through personally. So such details I can skip unless there is a question on those. So it shows actually the table. I'll just describe the table. Shows, see how deviated it was from the actual landmark plotted by the experts. Say if you can see, some of them are largely 0.77 mm, 0.72 mm, 0.5 mm, like such half mm variations or 1 mm variation maximum, except orbital, which was 2.42 mm in x direction and 1.24 mm in y direction. So others typically were about Bayesian also 0.46 mm on x direction and 1.45 mm on y direction. So roughly you can say within plus minus circle of 1 mm radius, you can accept the accuracy as possible and also accepted by the doctors. So that is, and then the rest of the job is to make those measurements which I showed you. I'm not showing you those because the accuracy of these landmarks itself is a challenge. And once you find these acceptable to within 1 mm, then they accept the angles and lengths measured by among those landmarks. So it's like finding then distances between the cities. It is like that, and accordingly they will treat you for your improvement of smile. So imagine the final word smile, which is related to these measurements. So I'll skip the rest of the details. I've already shown you the percentage of the results in terms of accuracy of recognition. So more or less I am done with it. Thank you for your patiently listening, and I'll be happy to answer some of the questions that we can take up. I'll be holding both three presentations. So any questions, please? Thank you.